Okay, we still in the same subject, but this time we will focus more about the classification. Okay, so we will speak now about how to use the Bayesian decision theory for a classification. That's why I don't like to give a break. Because I give break 10 minutes, then if every 1 or 2 minutes, some students coming and disturb us. So, Allahu Akbar. I think you will not die if we take 2 hours in one shot, yes, without a break, and I will give you the break at the end. So go and have fun after we finish. Because like this, I give you 10 minutes, okay, the regular break 10 minutes, but every 1 or 2 minutes, some students coming and coming and coming. And mashallah, the door is sound, it's very beautiful, yes? It's music, not sound. Okay, so let's look about some basic classification problem. Okay, so we have two categories or two collections of labeled. Annotated means it's already labeled, okay, data. We have to I just told you, don't knock the door. Okay. Directly, I'm sorry, then. I saw. Okay, let's continue. So, we have two categories. It's very similar species, okay, which is katydids and grass, grasshopper or something like this, grasshoppers, okay. In Arabic, we name both Jundub, yes. The it's jumping, yes. No, it's not Jarad in Arabic, Jundub. It's totally different species. It's looks similar, okay, but it's different. But this boss is from same type, but there's different category for them. So usually this one katydid have longer antenna, smaller body, and the grasshoppers have shorter antenna usually, and this the back of the body it's longer, and so on. But both it's life between the grass and jumping and so on. So our problem like this, we have two categories, each category labeled and have some features, okay? And when we have new insect like this, we need to categorize it. Is it katydid or grasshoppers? Which one? Depend on the features. Okay, so let's look to some features. For example, we have the color. Okay, we return to same subjects like before, yes, because now we will take examples about the classification. For example, green, brown, gray, and so on. And we have here this part, abdomen. We called it abdomen. So abdomen length, it's different from each of these species. All these features, the antenna lengths, we will focus in antenna lengths and abdomen lengths. Of course, we have many other features like leg lengths, leg counts, and so on. Okay. So let's take some data. This are two categories that we have. So as you can see, when we have abdomen length here with the antenna length. So as you can see, most of the katydid have longer antenna than hoppers. Okay. And about the abdomen lengths, we can, when you look to antenna, you have to look like this, yes? When you speak about antenna, here's the length. This one have length 1. This one have, okay. This have length 7, and this one's a count. We have 9. Later we will see it. So we can imagine that like this. If we look only for antenna lengths, we have this data. All this blue, it's a grasshopper, and this that have red dots, it's as a katydid. So if we look, let me just let you imagine. It's like this. We want to look only for antenna lengths. So antenna lengths, imagine it down. So if we just select and rotate. Hello. Oh, which one? It's not whole shape, but you can imagine it flat like this. Because we look where only for the antenna. So this one, what's the length? Or how many one we have? One with antenna length 1. We have here 1, 2, 3 with antenna length 2. We have 1, 2, 3, 4, 5, something like this with antenna length 3. With antenna length 4, we have 1, 2, 3, 4, 5, 6, 7, 8, 10, or something like this, or 9, and so on. This is the data for a grasshopper, and this is the data for katydid, that with antenna length 5, for example, we have only 1. Yes? So this is the meaning of the data. You have to flip it to understand what's the numbers here. Okay, you imagine it or still. So as you stated it, 1 when antenna links 5. So 1. This is the length 1. Here, the length 6, we have around 3. 5. Almost 6. And so to use this plot, okay, to use this plot for why you are looking the door? Only the antenna. Yes, here we have the links or the abdomen links and the antenna. We focus all on the net. You will have something like this. Yes. So what this mean? This mean when we have 1, when we have 2, when we have 3 antenna links, when we have 4, when we have 5, and so on. The antenna links, how many one we have from grasshopper, how many one we have from in the data set, in our data set, how many one we have from the KTD. So let's use. So actually classification is probability. Why probability? Because we will classify some things that we are not sure about it, yes? So depending on previous data, we will see what's the probability of the current item will be classified under which classification. So this is a curve that we had, and we have this insect, and we need to classify it. If we know that the antenna length is 3, this one, most probably, is it grasshopper or katydid? This is the question. So the probability of a specific classification given specific observed data or given specific feature. Yes. So we know that this one have length 3. So we should draw a line like this and take how many one we have from what's the red? You remember the red, it's katydid. And the blue is grasshopper. Yes, and this is the number of grasshopper for 3 antennas. So I think the numbers is 2 and 8 or something like this, or 2 and 10. So we have with antenna links 3, we have 2 katydid, and with antenna length 3, we have 10 of what? Grasshopper. So even without calculating the probability, it's almost what? Grasshopper, yes, with antenna length 3. To calculate the probability of being grasshopper with antenna length 3, it's 10. What's the 10? number of grasshopper with antenna length 3. It's 10 divided by the total. What's the total number here for length 3? It's 2 katydid plus 10. So it's 10 divided by 12. The total number 10. So katydid given length 3. It's how many katydid here? 2 divided by the total number. Okay, another example. We can try another example. With antenna lengths, for example, 6, it's here. So if the number here 2 and the number here 10. So the insect with antenna length 6, is it almost? Or what's the probability here? Probability of grasshopper with antenna length 6, it's equal. How much? Before the calculation. It's equal to, we speak about the grasshopper, which is the blue one. We said it's 2 divided by the total number, which is 12. And the probability of katydid given 6 antenna lengths, it's equal. How many katydid here? We have 10 divided by the total, which is 12. So it's almost katydid. Okay. Another example. Here. So maybe 5, for example, it's okay. If the numbers here 5 and 5. So we have 5 katydid and 5 grasshopper. What's the probability of being grasshopper given 5? It's equal 5. Which 5? How many grasshopper? 5. Let me take the number 4 here, so don't confuse between the 5 and the 4. Okay, so it's 5 divided by total number. What's the total number here at 4? It's 10. So it's equal 0.5. Probability of katydid given the length 5 for the antenna, it's also number of katydid, which is 5 divided by the total number, which is 10. So it's equal 0.5. This 4 is the length of the antenna, but we speak about the probability of this one, or probability of this one. It's the number of katydid divided by the total number. Okay. You can't see it or what?
She's saying 5 over 10, the total number of the grasshopper and the.
5 over 10. What's that?
Before, G over 4 equal 5 over. 5 over.
V over 4?
Yeah, we took the length for the length.
Is it 4 or 5?
No.
Because we wrote 5.
Yes.
Oh.
It's number of insect with this length. Okay, you confuse between the numbers. That's why I change it to 4. So you don't confuse. Let me repeat it for you, because seems you confused little bit.
Yeah, depends upon P of G given 5. Depends that you should change it before.
You mean I should write the full formula?
No. P
No. It's not about formula. This normal probability. It's not Bayesian formula. Okay, so probability of having crossover with length 3. Okay, it's equal. How many insects that we already know have in the data set have lengths 3? How many one? We have 10. Yes? Okay, divided by the total number of the insects, which is 12. Okay, when I take it here, 4, and here the numbers, which is 5 and 5. Yes? So 5G, 5K. Probability of G given 4, sorry. I wrote 5 because we gave at the beginning 5. Then I change it to 4. You leave everything and just stuck in a minor issue. Thus, I even did not look for it. It changed from my senior project groups. If you let's your view more wider, to be more wider, okay? So here another example, we have this insect with antenna length 7, okay? So 7, how many number in the data set we have with length 7? From grasshopper we have 3, from the kitty we have 9. So probability of grasshopper with antenna length 7, it's equal 3 grasshopper divided by the total, which is 12. Same issue for the katydid. Here when we have same numbers with an number 6 and 6 for both, so we have same probability. Let's move to the classifiers. Bayes classifier, we have many names. What's this one? Idiot, Bayes. It's not because it's idiot. It's very clever, but not idiot. But it's very simple. That's why it's named idiot or naive. Okay, or simple. All have same meaning. We will use this name. Naive or naive or pronunciation is not a problem for us. So it's very strong. Okay, may Allah bless you. Okay, so you know this actor? Yes. You are still young. If she's old little bit now. Okay, anyway, we speak about some simple Bayes classifier. Okay. And why we mention that it's simple? Because we will take simple form from the Bayesian or Bayesian decision theory. The simple form, it says, for example, here, true name or true name, it could be for male or, okay, this female persons. I know this one, actor, but I don't know this one. Okay. Maybe actor, I don't know him. So, if we have two classes, C1 male, C2 female, and we have to identify the gender or the sex of the person, okay? His name, true, or simply D, okay? We take only the first letter, D. And we want to classify, does he or she male or female? Usually we don't know this name because it's shared name. So let's usually to classify, we need to check which one have the most probability, yes? So probability of male and his name true, and the probability of female and his name true. Then the highest probability will be the classified one. We will classify the highest, depend on the highest probability, yes? Okay, so simple rule, probability of male true, it's equal to being male multiplied by probability of male divided by probability of true. This need usually the probability of the feature need too many calculation, yes? It's take calculation, too many calculation, but it's not affect actually the result of the classification. Why? Okay, tell me what's the probability of female true. It's equal what? Probability of true female multiplied by probability of female divided by probability of true or true. Look here. So if we get the number, then without divided by probability of true, it will make any change for the probability, means for the classification? No. For example, this one, the result of this one is 0.5. And the result of this one, for example, 0.3. So 0.5 divided by 0.3, it will give us some number. And for example, probability of this one, 0.3 divided by 0.3, because it's the same number down here and here. This number will be less than this number, even if you divide it by 0.3 or not. So it will not change our decision for classification. So for simplicity, we will simplify this rule. That's why it's named idiot or simple Bayes classifier or name. Why? Because we simplify it and remove this one from the rule. Because it will not affect the result of the classification, because for all the probabilities, means the posteriori probabilities, it will be same. So divided by the same number here and the same number here will not change the comparison between the probabilities. If this one greater than this one, okay? If X, for example, for simplicity, I will write it for you. If X greater than Y, probability of something, so X divided by Z, it's still greater than Y divided by Z. Yes? So remove Z or put Z, remove the division by probability of the feature from the down or from the division. Or put it will not change the final decision for the classification. Yes? So for simplicity, instead of, okay, we need to calculate it as a summation, so it's need too many calculation, we can simply ignore it. Yes, it will not affect the result. Okay, this is the officer, true, who's arrested you, not me, in 1997. Okay, maybe for driving fast or something. 1997, where I have been. I think in the 12th class or something like this, yes. You have been where? Not born yet. Yes, I think I was in the 12th class. Sorry? Okay. Is officer true, male or female? We know the general rule, this one, probability of the class given the feature, it's equals the feature given the class and so on. So what's the classes that we need? Male and female. What's the feature? The name. Its name? True, yes? Okay, so here's the data set. We have this data set from this office. We have the names True, Claudia or something like this, True, to Karin, Nina, Sergio Ramos. Sergio Ramos, yes. I don't like him. I don't like him. Messi, yes. I don't like him also. Yes, I was liking him, but not now. Oh, male, female. And we have this data set. Okay, give me the decision. How to take the decision? So we need to know the probability of, yes, probability of, okay, at least we have two focusing with us. Who said male here? You and you. We need to know if he or she, male or female. So probability of male with name, true or true. This one, we need to calculate it. And the probability of female, given the name, true. And then we take the greater value to as a class for our classification. Yes? So how to calculate this one depend on this rule. So probability of male and true, let me just make it male as M and true as T. It's equal probability of D true being male multiplied by probability of males divided by probability of true, but this one will not affect the result. Yes? So let's see the calculation. Probability of D given M. Okay. Y1 over 3. We have one true out of 3 males. This is the meaning of a probability. So you have to count how many D from how many males. This probability of males 3 males over the total number, which is 1, 2, 3, 4, 5, 6, 7, 8. So over 8. And this one drew, but we have 1, 2, 3. No, not the 3 drew. We speak about the drew. So from the males, how do we have 1 divided by the total number, which is 1, 2, 3 means. So 1 divided by 3 multiplied by 3 divided by 8. And this one down, it's not necessary. We can calculate it. Okay, probability of true, how much? 1, 2, 3 divided by the total number, which is 8. So it's not necessary. So this is a solution. Probability of male being true, it's 1 over 3. Why 1 over 3? 1 true out of 3 males multiplied by probability of true, which is we have 1. Not the probability of true. You stop it speaking with me. Probability of male. Okay? Probability of male. So we have 1, 2, 3 males over of the total number. So it's a 3 divided by 8%. Yes, this is the probability of male. So this one probability of male. This one probability of a true being male. Okay, this one probability of true. Yes, this one not important. However, we can calculate it easily from the data set. It's 1, 2, 3 true divided by 8%. So here at the down will not affect the result actually. This value is greater than this value. If you divide it by 3 to 8, it will be also this value greater than this value. So it's actually not affect the result. So we will not calculate the down one. We will not divide by it. That leads us to a general rule. If we have more than one feature, usually we don't have one feature. And teacher, since 2 weeks, and you are saying we could have more than one feature, we could have more than one category. Let's see more than one feature. Here we have many features. Okay, so we have here over 170 centimeter, yes or no? So usually when you want to identify a person, okay, the officer who arrested me, okay, I remember his name Drew, but we have many Drew. We have females, males, and so on. Okay? Okay. What's the color of the eyes? What's the hair length? And so on. So we have this data. The name, the 170, yes or no? The color of the eyes, we have blue, brown. The hair lengths, we have short, long. We could have short, long, medium also. Same will be. And the gender, we have male and female. So this is the general rule. We can use it. We ignore the down one. And here, probability of a specific category equal probability of this, the classifications that we need for the different category, or this is a general rule like this. If you have more than one feature, okay, so feature one feature for the same class. Okay, so probability of D that we need to classify it, male, female, and so on. Okay, with a specific category, this one. So we have feature one, feature two, feature three with probability of this feature with the specific category. We will use it too much, this one, for a class. Take example. So we have multiplication here. Actually, this one be multiplied at the end by probability of CJ. Why? Because this comes from the general rule. This one, we remove the down one. Yes? So probability of D1, D2, D3, D4, D5 with the same category multiplied by the probability of the category. So it's come from this general rule. We only remove what? The division of the probability. Why? Because we will have too many D, not the probability of, you remember when I said X, it's a vector, yeah, have many features. One of the, you will have problem. That's why we make it simple. We eliminate only this one. So the general rule for the naive Bayes classifier. So we name this one naive or naive Bayesian or Bayesian classifier. Okay, so what's this one? Thanks. What's your name that way I will forget tomorrow? Sam. Hassan. Hassan or Ihsan? Hassan. Hassan. Hassan, Hassan, Ihsan. Hassan. Where are you from? Suman. Okay, welcome. Okay, so the problem with naive classifier or naive classifier it assumes that all the features, for example, it's consider each distribution, it's dependent. In effect, however, in the real life, okay, maybe the fish, the smaller fish, for example, sea bass will have likeness different than the bigger one. But here we consider each feature independent. That's why it's not always accurate, but it's give you, it's depend actually at the end on the probabilities. So it's not really accurate. On the classification, actually, it's not 100 accurate. That's why, for example, one of our postgraduate student, he not create, design, classifier, make model from some algorithms. And when he tests the result, he said the accuracy 100. But I said it's not possible to be 100. If it's 100 means you are training and testing using same data almost, because you trained on this data, on the same data, of course you will get accuracy 100. But usually it's depend on probability, so it's not 100. It's not possible to get 100 almost. But close to 100. So probability of specific data or feature with a specific category, it's equal probability of feature with the category apply with probability of category itself. It's missing here. Should be written because in the real examples we will write it. Okay, so here we have more data about officer True. His eyes is blue eyes. He's over 170 tall and has long hair. This the name True, yes. So it's equal probability of over 170 given True multiplied the opposite. True. I have to remove this one. So according to this rule, it should be same order, yes? So it's a probability of over 170 with the true multiply by probability of this color with true, multiply by probability of hair length with the true, and so on. So probability of officer with female, it's probability of how many officer drew and multiply by how many. Okay, I wrote it in the opposite, yes. So this one, probability of drew with female. So this one, probability of, sorry, not the drew. Female. And what's the first feature? Over 170 multiplied by probability of eye color with female. Eye color, which eye color? It's a given for you. We give you some data feature. So probability of over 70, it's over 70, yes. So probability of yes and female. Here, over 70 equal yes. With, what's the category? Female. What's the category here? Female. What's the category here? Female. So over 70, yes. How many yes over 70 with female? Look here. Only 1, 2, 3, 4, 5. Over 70, yes. Over 70, yes. So 2 yes. Divide by how many female? 5. Okay. What's the eye? It's a blue. So probability of a blue and female. Okay. Female, it's still 5. The blue, we have 1, 2, 3. 3 females blue. So 3 divided by 5. Multiply by the hair. Probability with female. Okay, what given to you? That the hair is, why it's not working, this one? Okay, this one. It's long. So probability of long hair with female. Why? Because we speak about classification as female. So female 5, long hair 1, 2, 4 out of 5. So we multiply the probability, multiply by 4.5, multiply by probability of female itself, which is 5. Officer drew, is it male? So probability of first one, which is over 70, 170, and now we speak about and what? And male. So we speak about male here. Let me change the color. So we have 1, 2, 3 males. Okay. This 1, 2. So it's 2 over 3. What's this mean? 2. Yes. Longer than 170 over the total number of male, which is 3. Multiply by probability of the blue eyes and male. How many blue eyes? 1, 2. So multiply by 2 divided by total number of male, which is 3. Multiply by long hair and so over the total number of persons, which is 8. So at the end, you will see that this one will give you a numbers. I think it will be greater than this one. Yes. The number, maybe someone can calculate it. It's okay. Remove dot, multiply by 0.5 to make it just simple. So 2 multiplied by 3 multiplied by 4, yes. So, uh, 0.4 multiplied by 0.6 multiplied by 0.8. It's equal how much? Point 4.8, and this one will be smaller number. Almost it will be, I think, something like this. So 0.3, 1.3. Check these numbers. Is it give you more accurate probability or this one? See the difference here, not big difference when we have one feature, but more feature here give us, here's the difference become greater. So we are more sure now she's a female, yes? Why do you are looking too much to the time? We still have 3 minutes. I will not give another break. I will not give 2 breaks. One enough, but I will give you short break now while taking the attendance. So let me just, or I will take the attendance at the end 2 times because I don't want to stop the video. I usually stop the video when I take the attendance. Okay, usually here we have only 2 features, so we can calculate for each probability using a table like this. We could have more than one feature. For example, here for category animal, we have cat, and we have more than one feature for the color. So it's depend. You can have more than one feature for each category, and you can calculate it. Okay, about advantage and disadvantage. Comparing with other classifier, it's very fast to train because you need just single training, single scan, and fast to classify. Not sensitive for relevant features. So if some features will not make a change, it will not change the result. Okay. Handle any type of data, real, discrete data, streaming data. Okay, disadvantage, the main disadvantage, it's assume independent features. So if the features have some relations, okay, it will not take this relation between the features into consideration. We have bias application like real-time system to classify things on the real time, like categories for some text as spam filtering and so on, depend on the sequence of some words and the statements that can be in the email. Disease diagnosis recommendation system. We will take some examples for this. We have 3 types of a classifier. We will take examples for some of these types. Okay. Multi-nominal naive bias usually used to classify the documents. Depend on the some sequence of words presented in the documents. We can classify the documents. Like, is it belong to which field, for example, engineer or medical field or something, depend on the present frequency of the presence of the words in the document. We will take example for this one. What time we have to finish? 12:10? 12:10. I saw it. Okay, 12. From where you get it to 12? I will check here. No, it's better. Yes, you're correct. Okay. So we have Cronley or something like this naive Bayes. It's a Boolean prediction. This means yes, no prediction. Okay, depend on the data. Gaussian, it's depend on the normal distribution of the data. We name this curve a Gaussian distribution curve, yes? Let's take examples. This is the tips. You have to follow it. Let me make usually we have 0 frequency by adding 1 to the data in the data set. So we add for all the data +1 when we get the probability to avoid the 0, because we have multiplication. If you have some probability as 0 in the multiplication, what you will get the result? 0. But we need, okay, something, it's not exist, but we have to multiply its probability. If you get its probability 0, you will get the whole probability as 0. But if you get its probability 0.000001, you will not affect the final result of the probability. You will not get at it as 0. So to avoid this 0, we usually in the naive we put add 1 or we add 1. Okay. Try to add 1 when you have in the data set some data that could be 0. This is the most important one. Other ones, when we have it, we will speak it. Last one, it's speak about data must be pre-processed, okay, like feature selection and so on, to be appropriate for the naive pairs, because usually we don't have too many parameters, so we should have very specific when we select the features and the data. Quickly, yes, because we have to finish before the time. Yes.
on that or just for the zero?
If you add one, it must be for the whole. If you did not add, it's okay, but you should avoid the zero. So if you add not, and you don't want to change the result, so you will add for the all. Okay, let's go to the example. In this example, we want to take decision to play something, for example, tennis, football, or something like this, using data set. So the decision, it's a play or not a play. Okay, according to some weather condition data. Yes, so it's yes or no here. So we have this data set. So the problem, if the weather is sunny, we will play or not. We have this data set from the previous, okay? So if it's rainy, sunny, overcast. So we have for the outlook rainy, sunny, and overcast. For the play, we have two classes, yes or no, depend on this data. So we need to calculate if it's sunny, we will play or not. Let's organize this data in more simple. So we have the weather. Is it overcast, rainy, sunny? Yes. If it's rainy, here, rainy, and rainy. How many yes? How many no? We have 1, 2 yes, 1, 2 no. So, oh, it's a 3. So we have data here that is not clear. Let me just. I want. Oh, it's zoom everything, not zoom this one.
We just get, you know.
Okay, I will show it to you. Here, it's overcast, yes. So rainy, 1, 2, 3, 4. Is it 4 or 5? 1, 2, 3, 4. It's written 5 here. No, this overcast. I did not focus. So it's overcasting 5, yes. Overcast, yes, yes, yes. Overcast, yes. For the rainy, we have 2 yes, 2 no. For the sunny, we have 3 yes, 2 no. So we calculate some probabilities here. For overcast, we have 5 overcast out of 14, the total number here. The total number is 10 yes, 14 no, so it's from 0 to 13, the index, so it's 14 totally. So how many overcasts? We have 5. 5 divided by, the total number is 14. Rainy, we have 4 divided by 14. And sunny, we have 5 divided by 14. So it's a probability for overcast, rainy, and sunny. For no, we have 4 no out of total 14. For yes, we have 10 yes over of 14. The total yes and no together, it's 14. We calculate some probabilities here. So let's apply the Poyet's theorem. We need the probability of yes and sunny. It's equal probability of sunny yes multiplied by Probability of yes divided by probability of sunny. So this one, probability of sun and yes. Okay, you will go to the yes. How many yes we have? 10. How many sunny we have? 3. So it's a 3 out of 10. So what's point? Probability of sunny. We calculate it here. Yes. So probability of yes. What's the probability of yes? 10 divided by 14. Then you will calculate the multiplication. Okay, this same after the calculation for no and sunny. This for yes, that one. This for no and sunny. So we get 0.4 and 0.6. So you will play or not? Most probably yes. Okay. Let's go to this example, last example, and we will finish. This also important example, but have just 5 minutes. Okay. Or let's take the attendance. I will give this example at the beginning of next lecture. Okay, just give you some information. This example for the other type, which is nominal or nominal nav, it's for document topic. So we will classify the document topic. Is it about China or Chinese or Japanese, depending on the frequency of the words. So we have training set and test set. So depend on training set, data from the training set, we will classify number 5 document. Okay, depend on the previous data. I will stop here because I will show you here the effect of adding 1. Okay, here we have to add 1 to avoid 0 because we have multiplication in the probability. If you did not add 1, for example, here, you will have 0 probability. When you multiply here 0, 0, 0, 0, 0, 3, 0. Okay, and this one will be 0, then you don't have classification. That's why we will add 1 for the data. I will give you the rule later. We use it with some classification, not always, okay? So you have to focus. Let me just, okay. Take the attendance quickly. Just let me stop the recording.